You know, usually when we talk about a medical diagnosis, there's this expectation of clinical precision.
Right.
It feels very engineering adjacent. Like you break your arm, the X-ray shows that jagged white line, and the doctor just points at the film and says, "There it is."
Yeah, and it's comforting, right? Because it's completely observable. We inherently trust systems where the state space is visible and easily categorized. You have the ground truth right there in front of you.
Exactly. But then, and this is the wild part, you step into the world of optimization and unsupervised machine learning, and suddenly it's like someone takes a sledgehammer to that X-ray machine.
Absolutely.
We're no longer looking at a clean, observable binary. We are looking at a landscape that is mathematically murky. You're trying to find a global optimum on a topological map you can't even see. It's completely shrouded in fog.
Right, and every single step you take
Mm-hmm.
might be leading you off a cliff or, into a total dead end.
It is the absolute definition of navigating in the dark.
It really is. You are forced to make these massive global decisions using nothing but highly constrained local information.
And that is exactly why we are here today. We're welcoming you to this deep dive. And look, we know exactly what your mission is right now. You are staring down the barrel of a rigorous graduate level exam in machine learning.
Think Georgia Tech style.
Yeah, exactly. And let's be totally honest with each other here. Rote memorization is not going to save you.
Definitely not.
Memorizing the pseudocode for K-Means or AdamW, that won't cut it when the exam specifically asks you why one algorithm fundamentally fails where another succeeds.
Right. Or how changing a single hyperparameter alters the mathematical geometry of the entire space you're searching.
Yeah, that is the critical threshold for this material. Mastering this level of machine learning isn't about memorizing a table of contents.
I mean, it's about understanding the intertopic connectivity. It's about seeing the evolutionary logical tree of these algorithms.
Because every single algorithm we are going to unpack today was invented as a direct response to its predecessor hitting a wall.
Exactly. A mathematical or computational brick wall.
Mm.
If you understand the wall, the algorithm naturally derives itself.
So that is the mission today. We are mapping the logical flow and the why behind the progression of algorithms in optimization and unsupervised learning.
The big task.
It is. And to do this, we are pulling from a massive stack of sources. We've got comprehensive lecture transcripts, deep dive course summaries, a highly specialized 2025 paper detailing the mathematical journey from plain stochastic gradient descent to AdamW.
Which is a fascinating paper, by the way.
Oh, it really is. And we also have intricate notes on information theory and extensive materials on Bayesian inference, manifold learning, and feature transformation.
It's an incredibly dense stack. But the underlying narrative is beautiful.
It really connects, doesn't it?
It does. Seemingly disparate topics like how a neural network updates its weights during training and how an unsupervised algorithm groups entirely unlabeled data points. They're connected by the exact same principles of probability distributions and high-dimensional geometry.
Okay, let's unpack this from first principles. If you're sketching this out for your exam, you want to start with gradient optimization.
Right.
So imagine you are dropped onto an unknown massive mountain range in pitch black, dense fog. Your objective is to get to the absolute lowest altitude point in the entire mountain range.
And in machine learning, this maps directly to the foundational concept, empirical risk minimization.
Let's define the axis of that analogy for a second.
Sure. So the landscape you are standing on is your loss function. The altitude at your current position, that's your error rate based on your current parameters.
So the lower you go, the better your model performs on the training data.
Exactly. But because this landscape is incredibly complex, living in millions of dimensions, and often highly non-convex.
Meaning it's full of jagged peaks and valleys, right?
Yeah, exactly. Because of that, you cannot simply use calculus to find the lowest point analytically. Setting the derivative to zero and solving just isn't computationally possible for a massive neural network.
So we have to take iterative steps. And the only tool we have in our backpack is a compass that tells us the immediate slope of the ground directly beneath our feet.
Right.
That compass is the stochastic gradient.
And it's a stochastic gradient because, well, in practice, calculating the true gradient over your entire massive data set for every single step is just way too slow.
So you estimate it.
Right. You estimate the slope using a small mini batch of data.
Okay, so I check my compass. It says the steepest way down is to my left, and I take a step in that direction.
And the physical distance of the step you take, that's your learning rate?
On the surface, that sounds like a solved problem. I mean, just keep stepping down. But if I'm taking the exam and the professor asks why stochastic gradient descent SGD is insufficient for deep learning, what's the mathematical failure point?
The failure point really is an assumption. SGD implicitly assumes that the landscape is relatively smooth and uniform in all directions.
Like a nice, gentle bowl.
Exactly. But deep neural networks create loss surfaces that are notoriously ill-conditioned. They look like steep, narrow ravines.
Oh, I see.
Imagine you're standing in a gorge. The rock walls rise sharply on your left and right, but the valley floor slopes very, very gently downward right in front of you.
Okay, so if I check my compass in that gorge, because the walls to my left and right are so steep, the gradient calculation is going to overwhelmingly point toward the walls.
It's going to scream at you to go left or right.
Right, because that's where the most dramatic slope is, completely drowning out the tiny downward slope of the valley floor itself.
And that leads to the classic zigzag problem.
Ah, okay. Walk us through the zigzag.
So you take a step based on that steep gradient, and because your learning rate is fixed, you end up taking a massive step up the opposite wall of the ravine.
Oh, man. So now you're high up on the other side.
Yep. You calculate the gradient again, and the compass screams to go back the other way. You violently oscillate back and forth across the ravine walls, making almost zero forward progress down the gentle slope of the actual valley.
It's mathematically exhausting.
It is, and it practically stalls your training entirely.
So we need to dampen the zigzag. If I'm thinking about physics, the way to stop something from wildly changing directions is to add inertia, like momentum.
Exactly.
Instead of taking isolated steps, imagine we drop a heavy iron ball into that ravine. The ball doesn't instantly snap to a new direction just because the slope changed for a split second.
Yeah.
It has physical momentum carrying it forward.
This is exactly what Pollack introduced in 1964 with heavy ball momentum. Mathematically, it's brilliant, but simple.
How does it work under the hood?
Instead of just using the current gradient to update your parameters, you maintain an exponentially decaying average of your past gradients.
Let's trace how that behaves in our ravine analogy.
Okay, so the gradients pointing left and right are constantly alternating left, right, left, right. When you average those out over time, they cancel each other out.
Oh, wow. So the cross-ravine oscillation just goes to zero.
Exactly. But the tiny gradient pointing forward, down the valley, that one is consistent. Every single step, there's a tiny pull forward.
So when we average that over time, it cumulates.
Yes. The momentum dampens the conflicting directions and amplifies the consistent direction. You stop zigzagging and start accelerating down the valley floor.
That feels like a solid fix. But wait, if I keep accumulating momentum, there has to be a breaking point, right?
What do you mean?
Well, if the heavy iron ball is picking up speed down this valley and suddenly the valley curves sharply, or we hit the actual global minimum, isn't the ball just going to launch right over the edge? Or completely overshoot the minimum because it has too much built-up speed?
That is the exact mathematical vulnerability of Pollack momentum. It is essentially blind.
What?
Yeah. The update rule calculates your current gradient, adds your accumulated momentum, and just takes a blind leap.
So it doesn't see the cliff coming.
Right. And Yuri Nesterov saw this flaw. He introduced Nesterov accelerated gradient, or NAG. Nesterov asked a fundamental question. If we know exactly where our momentum is about to carry us, why don't we look before we leap?
But wait, how do you look ahead if you're in the fog? You don't know what the landscape looks like.
You don't know the whole landscape, but you do know your current momentum vector. You know precisely what your position will be if you just apply the momentum alone.
Ah, okay.
So, AG mathematically peaks at that future look-ahead point. Instead of calculating the gradient where you are currently standing, it calculates the gradient at the future point where the momentum is about to take you.
Oh, I see. So if my momentum is about to launch me out of the valley and up a steep hill, the gradient at that future point is going to be pointing sharply backward, down the hill.
Precisely. That future gradient pushes back against your momentum before you actually take the step.
It's like an automatic braking system.
Exactly. It corrects your trajectory,
Yeah.
allowing you to carry high momentum when the path is clear, but slamming on the brakes right before a curve or a minimum.
That's a beautiful geometric trick. Okay, so Nesterov gives us a really smart guided ball, but there's still a glaring issue here if we're dealing with deep learning.
Which is?
We are using a single global learning rate. The pace plan is exactly the same for every single parameter in the model.
Right.
But if I have a network with 10 million parameters, surely some features show up constantly and some features are incredibly rare.
And this is a critical transition point for your exam preparation, moving from global learning rates to per-parameter adaptivity.
Let's use an example.
Think about natural language processing. The word "the" appears millions of times. The gradient updates for the weights associated with "the" will be massive and frequent.
Sure.
But a rare word like obfuscate might appear 5 times in your entire data set.
So if I set my global learning rate small enough so that the weights for the don't explode and destabilize my model, that learning rate is going to be infinitesimally small for obfuscate.
Exactly.
I'll literally never learn the rare features because the steps are too tiny. But if I turn the learning rate up to learn the rare features, the frequent features will just blow up.
Which is why John Ducci and his team introduced AdamW. It stands for Adaptive Gradients. The insight was to scale the learning rate for each individual parameter inversely to its historical gradient size.
Let me make sure I have the mechanics of this right. AdamW keeps a running sum of the squared gradients for every single parameter.
That's right.
So for the word "the," it has huge gradients. We square them, we add them up, and this running sum gets massive. Then AdamW takes the global learning rate and divides it by the square root of that massive sum.
Correct. The denominator for frequent features becomes huge, which aggressively shrinks their effective learning rate. They take careful, tiny steps.
But for our rare word, obfuscate, the gradients are tiny, the sum of squares is tiny, so the denominator is tiny.
Exactly. Its effective learning rate stays relatively large, allowing it to take meaningful steps when it finally does appear.
It perfectly balances the feature space. But wait, if I look at the math for AdamW, you said it keeps a running sum of squared gradients.
Yes.
A squared number is always positive. If I just keep adding positive numbers together for thousands of epochs.
The sum approaches infinity.
Wow.
This is the fatal mathematical flaw of AdamW. Irreversible shrinkage.
Because it never forgets.
Right. As training progresses, the accumulated sum in the denominator strictly grows. It never shrinks. Eventually, the effective learning rate for every single parameter becomes microscopic.
The algorithm simply stops learning.
It becomes effectively paralyzed, often long before it has actually reached the global minimum.
It suffers from catastrophic amnesia by carrying too much historical baggage. So how do we fix a running sum that grows infinitely? We need a mechanism that forgets the distant past.
And that mechanism is RMS-Prop, developed by Jeff Hinton. RMS-Prop essentially says, we only care about the recent curvature of the landscape.
Okay, so it throws out the old data.
Not entirely. Instead of a raw running sum of squared gradients, RMS-Prop uses an exponential moving average, or EMA, of the squared gradients.
Let's define the EMA for the listener, because the decay rate usually denoted as gamma is crucial here. It's not just a hard cutoff window where we only look at the last 100 steps, right?
Right. An EMA smoothly decays the influence of older gradients. At every step, you take a fraction of your old average, say 0.99, and add a small fraction of your new squared gradient, like 0.01.
So the denominator reflects the landscape you are currently in.
Exactly. If you leave a steep ravine and enter a flat plateau, the old massive gradients from the ravine are slowly forgotten as the EMA decays. Your learning rate scales back up, allowing you to traverse the plateau efficiently.
So RMS-Prop solved the paralysis of AdamW while maintaining per-parameter adaptivity.
It did.
Which brings us to the king of the hill, the algorithm that practically runs modern deep learning, Adam.
Yes, Adam.
If I'm tracing the logical flow, Adam isn't a completely new paradigm, is it? It's more of a synthesis.
That's a great way to put it. It takes the heavy ball momentum we use to fix the zigzag, which Adam calls the first moment, and combines it with the EMA of squared gradients from RMS-Prop, which it calls the second moment.
That is the core of Adam. It has inertia to push through ravines, and it has adaptive learning rates to balance rare and frequent features.
But there's a catch. If you just mash momentum and RMS-Prop together, it fails spectacularly in the first few epochs.
Really? Why?
Because you have to initialize those moment trackers at 0.
Ah, so at step 1, the EMA for both momentum and the squared gradients is essentially 0.
Right. And even after a few steps, because that decay rate is so high, like 0.99, the trackers are heavily biased toward their starting value of 0.
And if your denominator, the second moment tracker, is artificially close to 0, you are dividing your learning rate by a tiny fraction.
Exactly. Your initial steps will violently explode. Your model will diverge immediately.
So how did they fix it?
The authors of Adam introduced bias correction. It's a mathematical scaling factor that boosts the moment estimates early in training to counteract the fact that they started at 0.
Oh, that's clever.
And as training goes on, the bias correction terms naturally decay to 1 and just get out of the way.
That is incredibly elegant. So we have Adam, it seems perfect. But our source stack includes a highly specialized 2025 paper detailing the critical transition from Adam to AdamW. What was the hidden flaw in Adam that necessitated AdamW?
This is one of the most fascinating pieces of mathematical detective work in recent machine learning history, and it is a prime target for a high-level exam question.
Let's hear it.
For decades, the ML community used the terms L2 regularization and weight decay completely interchangeably.
Because mathematically, under plane stochastic gradient descent, they are identical, right?
Under plain SGD, yes. Let's trace it. L2 regularization is a modification to your loss function. You add a penalty term based on the sum of the square weights.
So the math basically says if a weight gets too large, punish the model.
Exactly. When you take the derivative of that L2 penalty during backpropagation, it simply adds a term proportional to the weight itself to your gradient.
And weight decay, on the other hand, is a modification to the update rule. It completely ignores the loss function. It just says, every time I update a weight, I'm going to multiply it by 0.99 to shrink it a little bit.
That's it. In plain SGV, adding L2 to the loss or adding weight decay to the update rule result in the exact same mathematical operation.
Okay, so where's the flaw?
Well, Ilya Loshalov and Frank Hutter proved that under adaptive preconditioning, meaning algorithms like Adam, they violently diverge.
Walk me through the divergence. What happens when we put L2 regularization into Adam?
Think about the weight update equation in Adam. You take your gradient, which now includes that L2 penalty, and you divide it by the second moment tracker, the adaptive denominator. Let's go back to our rare feature versus frequent feature. For a frequent feature, the denominator is huge. So the gradient and the L2 penalty mixed inside it gets divided by a huge number.
So the penalty shrinks.
Exactly. And for a rare feature, the denominator is tiny. So its L2 penalty gets divided by a tiny number, which actually scales the penalty UP.
Oh, wow. It completely breaks capacity control.
Completely. By using L2 regularization inside Adam, you are actively punishing rare features far more aggressively than frequent features, just for being rare. It tangled the regularization with the gradient scaling.
So how does AdamW decouple it?
AdamW abandons L2 regularization entirely. It removes the penalty from the loss function. Instead, it applies pure weight decay after Adam has done all of its adaptive gradient scaling.
It mathematically separates the optimization from the regularization.
Yes. This single insight restored uniform capacity control and is largely responsible for why we can train massive, stable large language models today.
That is a perfect progression. From SGD's zigzag to momentum's inertia to NAG's look ahead to Adagrad's adaptivity to RMS prop's memory window to Adam synthesis to AdamW's decoupled regularization.
It's an amazing chain of problem solving.
We have built an incredible, highly tuned vehicle to navigate this foggy mountain. But what if the mountain itself fundamentally breaks our assumptions?
Like what?
What if the loss landscape isn't made of continuous slopes? What if it's covered in sheer, discrete cliffs like a staircase? Or what if our fitness function is a black box and we can't take a derivative at all? Our compass, the stochastic gradient, just spins uselessly.
That is where the gradient optimization paradigm completely collapses. If the function is non-differentiable, you simply cannot use calculus. We have to abandon the compass and transition to a completely different class of algorithms.
We enter randomized optimization.
Exactly.
Escaping the matrix.
Instead of calculating a slope, we are going to generate potential solutions, test them, and blindly search. If you're outlining this on your exam, the absolute baseline, the simplest algorithm here is hill climbing. And its logic is rudimentary. You pick a random point on the map, you look at your immediate neighbors in all directions.
Okay.
If one of them is higher, assuming we are now maximizing a fitness function rather than minimizing loss, you take a step to that higher point. You repeat this until every neighbor is lower than you.
And the flaw is so immediate, it's almost painful. Local optima.
Yes.
If you climb to the top of a small, mediocre hill, every step around you is down, the algorithm terminates, it declares victory, and stops, completely unaware that Mount Everest is sitting just a mile to the right.
The lecture transcripts actually feature a brilliant concrete quiz to illustrate this vulnerability. They mapped out a one-dimensional input space from x equals 1 to x equals 28.
I remember this.
The fitness function was this chaotic, jagged, drunk sawtooth wave with multiple peaks, but only one true global maximum.
Right, and the quiz challenged the students. If you drop a point randomly on this x-axis and use hill climbing, how often do you find the global maximum?
And the math proved that starting from almost any position, you climb to a local suboptimal peak in about 5 steps and get permanently stuck.
It perfectly demonstrated the concept of basins of attraction.
A basin of attraction is a vital topological concept. Imagine the landscape as a plastic mold, and you drop a marble onto it. The basin of attraction for a specific peak is the entire surrounding area where gravity would cause that marble to roll up to that specific peak.
If the basin of attraction for your global optimum is massive, hill climbing will likely fall into it and succeed.
But in complex ML problems, the global optimum is a needle in a haystack. Its basin of attraction is tiny. If you drop a marble randomly, the probability of hitting that tiny basin is near zero. So hill climbing fails.
So what's the immediate band-aid for this?
Random restart hill climbing. Once you get stuck on a fake peak, you just teleport to a completely random new coordinate on the map and start climbing again. You do this 1,000 times and keep the best result.
It works, mathematically speaking. Given infinite time, random restarts will find the global optimum, but it is wildly inefficient.
Think about the geometry of what you're doing. When you randomly teleport, you throw away all local progress. You suffer from complete geometric amnesia.
This raises the next critical constraint. Can we explore the landscape, escape a local optimum, without starting entirely over every single time?
And the solution to that is simulated annealing.
I always appreciated this one because the analogy is so visceral. It comes from metallurgy, right?
It does.
To make a steel sword strong, a blacksmith doesn't just cool it slowly. They heat it up to a glowing red, let it cool a bit, heat it again, and so on.
Right. The intense heat adds energy to the system, allowing the iron and carbon molecules to bounce around violently, breaking out of bad, brittle, crystalline alignments.
And as it slowly cools, they settle into a perfectly optimal, incredibly strong lattice structure.
In optimization theory, that metallurgical process maps directly to the exploration versus exploitation trade-off.
Let's define those for the listener.
Exploiting is taking the best local step, greedily climbing the hill right in front of you. If you exploit too aggressively, you overfit your path to the local landscape and get trapped on a tiny hill. And exploring. Exploring is wandering randomly, ignoring the immediate slope to map the broader space.
So how does simulated annealing balance this mathematically?
It simulates a temperature variable. When the temperature is high early in the run, the algorithm is deliberately allowed to take downward steps. It's allowed to take worse steps.
Oh, wow. So if it's on top of a local hill, the high temperature gives it the energy to walk down off the hill through the valley and wander around.
The underlying math here uses the Boltzmann distribution from statistical physics. The probability of accepting a worse step is a function of both how much worse the step is and the current temperature.
At high heat, the probability distribution of your next move is incredibly flat. You might step anywhere.
Exactly. But then we implement a cooling schedule. As time goes on, the temperature drops. The Boltzmann probability distribution tightens.
The algorithm becomes greedier.
Yes, it accepts fewer and fewer downward steps. By the time it's freezing, it acts exactly like standard hill climbing, rushing to the top of whatever massive peak its earlier exploration led it to.
It's an elegant way to maintain state without getting stuck, but there's still a glaring limitation. Simulated annealing only tracks a single point moving through space. It's a lonely explorer.
Right. What if we could search the space in parallel and have those parallel points share information?
Which brings us to genetic algorithms, or GAs. We move from a single point to a massive population of points.
We evaluate all of them. We take the best performers, the fittest, and we mutate them slightly, which is essentially local parallel hill climbing.
And then we perform crossover. We take half the genes or features of one great solution and combine them with half the features of another great solution, hoping to spawn a global optimum.
And here is where the lectures provide a profound level of depth that you absolutely need for the exam. The professor drops a massive caveat about genetic algorithms.
This is crucial.
The mechanism of crossover secretly relies on a massive, often unverified mathematical assumption: locality.
Let's unpack the locality assumption, because if you get this wrong, GAs basically destroy your data.
Locality is the assumption that subcomponents of your input space can be optimized independently of one another.
Like, imagine a 100-feature vector. Crossover assumes that if features 1 through 50 are highly optimized in parent A, and features 51 through 100 are highly optimized in parent B, snapping them together will yield a highly optimized child.
Exactly. But what if feature 49 fundamentally depends on feature 52? What if changing one breaks the other?
Then your locality assumption is violated.
Right. If the features are highly interdependent, cutting the vector in half and swapping parts doesn't combine good traits. It shatters the structural integrity of the solution.
You take the front half of a Ferrari and the back half of a Porsche, and you don't get a hypercar. You get an undrivable pile of scrap metal.
I love that analogy. And that leads to the ultimate realization about all of these randomized algorithms. Hill climbing, simulated annealing, GAs, they all suffer from a form of structural amnesia.
Structural amnesia.
Yeah. They might remember the coordinates of the best points they found, but they don't learn anything about the actual topology of the search space. After a million iterations, they don't know why certain areas are bad and certain areas are good. They don't understand the dependencies.
Which brings us to the pinnacle of this logical progression, MI-MIF, mutual information maximizing input clustering.
MES looks at the amnesia of previous algorithms and says, instead of tracking discrete points, let's mathematically model the probability distribution of the optimum space itself.
It attempts to learn the underlying structure of the landscape. Okay, if I'm taking the exam, I need to know exactly how MEF models that structure. It doesn't just guess, right?
No, it generates a sample of points, finds the subset of the absolute best performers, and then it builds a dependency tree based on those top performers. It figures out how the features relate.
It might learn mathematically, in all of our best solutions, whenever feature A is high, feature B absolutely must be low. It captures the correlation.
But generating that tree requires serious computation. MIAC has to calculate the mutual information between every single pair of features and then run Prim's algorithm to construct a maximal spanning tree.
Wait, let's pause there so we don't leave the listener behind. What exactly is Prim's algorithm doing in this context?
Conceptually, Prim's algorithm is a way to connect a set of nodes, in this case your features, into a single connected graph without any closed loops. And it does this ensuring that the total weight of the connections is maximized.
So MIMIC calculates the mutual information, the strength of dependence between all pairs of features.
Right. Prim's algorithm starts with one feature, looks for the feature with the highest mutual information to it, and draws a line between them. Then it looks at those two, finds the next most strongly connected feature, and adds it to the tree.
And it just repeats this until all features are connected in a way that captures the strongest statistical dependencies of the optimal space.
Exactly.
Okay, but calculating pairwise mutual information for thousands of features and then running graph algorithms on top of that at every single iteration, that has to be astronomically slow compared to just tweaking a point in simulated annealing.
It is orders of magnitude slower per iteration, and the transcripts emphasize this heavily.
So why ever use MIMIC?
Because while the cost per iteration is high, the total number of iterations required to find the global optimum drops drastically.
I see. You use MIMIC when evaluating the fitness function itself is the bottleneck.
Yes. If your fitness function is simple math, use simulated annealing. But what if evaluating a single point requires running a complex fluid dynamics simulation for a rocket nozzle?
Or what if it requires a human in the loop to grade an output?
Exactly. If the fitness evaluation takes an hour, you cannot afford to take 100,000 blind random steps. You need an algorithm that spends computational time learning the space so profoundly that it can find the global optimum in just 50 highly informed structured steps.
IIMX trades cheap, blind steps for expensive, structurally aware steps. That makes perfect sense. But to truly understand how IIMX builds those trees, we have to transition to the underlying math. We keep throwing around the phrase mutual information.
Right.
How do we rigorously mathematically measure structure or dependency between variables? This brings us to information theory.
Formulated by Claude Shannon in the 1940s, information theory is the language of structure. To grasp it, we need to build from the ground up.
The foundational unit is a random variable.
Yes. This is an object that takes on unpredictable values according to a probability distribution like the roll of a die or the value of a pixel in an image.
We describe random variables using moments. The first moment is the mean, the expected average value.
And the second central moment is the variance, how wildly the values swing away from the mean.
But mean and variance don't tell us how much information is in the variable. For that, we need entropy. Entropy is the fundamental measure of pure randomness or uncertainty contained in a single variable.
Let's use Shannon's original context to explain this. Data compression and communication channels. Imagine you have to transmit an image over a network.
Okay.
If the image is a perfectly clear, cloudless blue sky, the entropy is near zero. The pixel values are entirely predictable. You don't need to transmit the data for all 1 million pixels. You could highly compress it and just send the message, all pixels are blue.
The uncertainty is zero.
Right. But what if the image is pure TV static, random noise?
Then the entropy is at its absolute mathematical maximum. Every single pixel is an independent surprise. You cannot compress it. You have to transmit every single bit because the uncertainty is absolute.
Okay, so entropy measures the chaos of a single variable. But MIM is building trees connecting multiple variables. We need a way to measure relationships.
That is mutual information. Mutual information measures the reduction of randomness or uncertainty in one variable, given that you have observed another variable.
Going back to our image transmission. Suppose we are transmitting a picture of a human face. If I isolate the pixels corresponding to the left eye, they have a certain entropy.
Right.
But what if I already transmitted the pixels for the right eye? Because human faces are highly symmetrical, knowing the exact structure of the right eye dramatically reduces my uncertainty about the left eye.
The entropy drops.
Exactly. The amount by which the uncertainty drops is the mutual information between the two eyes. If they were totally unrelated, like a pixel in the background and a pixel on the nose, knowing one tells you nothing about the other.
The mutual information is zero.
Yes. So MIM key is scanning the features of the best solutions, looking for pairs of features that have high mutual information and connecting them in the tree.
But what's the actual engine calculating that? The transcripts point to a deeper mathematical truth. Mutual information is just a specific application of Kullback-Leibler, or KL, divergence.
KL divergence is a concept that haunts every corner of advanced machine learning. It is a metric that measures the distance, or the difference, between two probability distributions. How much does distribution P diverge from distribution Q?
And how does that map to mutual information?
In mutual information, we are using KL divergence to measure the distance between two very specific distributions. First, the joint probability distribution of two variables, how they actually behave together in reality.
That's not good.
Second, the product of their marginal probabilities, which represents how they would behave if they were completely statistically independent.
I see. So if the variables actually are completely independent, like the outcome of two different coin flips, their joint probability is mathematically identical to the product of their individual probabilities.
The two distributions are exactly the same. The KL divergence between them is zero. Therefore, the mutual information is zero.
But if they are highly dependent, like the left eye and the right eye, those two distributions wildly diverge. The joint distribution is incredibly tight, while the independent assumption is a massive, blurry space.
The KL divergence becomes large, yielding a high mutual information score. MIMI calculates this KL divergence across the board, finds the maximum divergences, and uses Prim's algorithm to lock in the dependency tree.
It is a masterclass in using probability to map topology. This is where the intertopic connectivity becomes stunning. We've been using probability distributions in structure to find optimal solutions.
Right.
But what if we don't even have a fitness function? What if we aren't trying to solve a problem, but rather we are just handed a massive, chaotic database of raw, unlabeled data and told to find the hidden structure inside it?
Then we leave optimization and enter unsupervised learning and clustering. The goal is to group objects' rows in your database based on their inherent mathematical relationships.
And exactly like optimization, the algorithms here evolve by systematically failing and forcing a mathematical fix.
Let's chart the evolution of clustering for the exam. You want to start with the most naive approach, single-linkage clustering, or SLC.
It's a bottom-up agglomerative approach.
Yeah.
You start by putting every single data point into its own isolated cluster. Then you look across the entire space, find the two clusters that are closest together, and merge them.
And you just repeat this process, merging the closest pairs, until you've reduced the data down to the number of clusters you want.
But the critical vulnerability lies in how SLC defines closest.
Right. The distance between two clusters is defined exclusively by the distance between their two nearest edge points. It completely ignores the bulk of the data inside the clusters.
And that leads to the classic failure state of SLC, the chaining effect. Imagine you have a dense circular grouping of points, but there's a thin trail of noisy points leading away from it.
Because SLC only looks at the nearest neighbor, it will grab a point in the circle, then grab the nearest point in the trail, and it will just keep merging along the trail.
It creates this giant snake-like chain that stretches across the feature space, completely failing to recognize the dense, compact circle as a primary geometric structure.
It just follows breadcrumbs into the woods.
To fix the chaining effect, we need an algorithm that stops looking at the edges and starts looking at the center of mass. We need an algorithm that cares about the gravity of the cluster.
That brings us to K-Means. And interestingly enough, K-Means isn't really a clustering algorithm in its purest form. It's an expectation maximum optimization algorithm dressed up as a clustering tool.
Let's walk through the mechanics. You have to tell it K the number of clusters you believe exist. You drop K completely random center points, called centroids, into your data space.
Step 1. Every single data point looks at all K centroids and assigns itself to the one it is mathematically closest to.
Step 2. Now that you have these initial rough clusters, you calculate the mathematical center of gravity for each group of points. You then physically move your centroid to that new center of gravity.
And you just tick-tock back and forth. Reassign the points, move the centers. Reassign the points, move the centers. Every step minimizes the squared error between the data points and their assigned centroids.
It is effectively a specialized form of hill climbing.
And because it's a form of hill climbing, it inherits hill climbing's greatest weakness: local optima.
The transcript points out a very specific, dangerous quirk in K-means initialization. K-means can get parallelized with zero progress if those initial random centroids fall in the wrong place.
Yes, the classic A, B, C, D, E, F trap. Imagine you have 6 points laid out in a straight line on a 1D axis. There are clear gaps, and the visually obvious answer is 3 clusters of pairs: A and B, C and D, E and F.
So you set K equals 3.
But because initialization is random, imagine your 3 centroids land exactly on points A, B, and C.
Let's trace the math on that disaster. Step 1, point assignment. Centroid 1 is on A, so it claims point A. Centroid 2 is on B, so it claims point B. Centroid 3 is on C. Point C is obviously closest to it.
But what about points D, E, and F?
Centroid 3 is the rightmost center. It is mathematically the closest centroid to D, E, and F as well. So centroid 3 claims all 4 points: C, D, E, and F.
Now, step 2. Move the centers to the mean. Centroid 1 is just point A. The mean of A is A. It doesn't move. Centroid 2 doesn't move from B. Centroid 3 calculates the mean of C, D, E, and F and moves to the middle of that pack.
And on the next tick-tock, nothing changes. The distances remain relatively the same. A and B are totally marooned in their own tiny clusters, and the algorithm converges instantly on a terrible, highly skewed model.
It is mathematically parallelized on step 2. To fix this, you have to run K-means with random restarts, running it dozens of times with different seeds and keeping the one with the lowest overall variance.
But even with restarts, K-means has a deeper philosophical flaw. It forces hard assignments. It is entirely binary.
If a data point is sitting exactly equidistant between centroid 1 and centroid 2, K-means forces it to pick one. It draws a brutal, rigid line in the sand, assuming 100% certainty where there is none.
Which, statistically speaking, is incredibly arrogant. If a point is in the middle of a massive feature space, we should acknowledge the uncertainty of its origin. We need soft clustering.
And this provides the perfect logical bridge to expectation maximization, or EM. EM is the probabilistic evolution of K-means. Instead of relying on rigid geometric distances, we bring in maximum likelihood estimation, or MLE.
We have to derive this from first principles. With EM, we assume a generative model. We assume our data wasn't just randomly splattered on the graph. We assume it was generated by a mixture of K hidden probability distributions, usually Gaussian bell curves scattered across the space.
Our goal is to find the parameters, the means, and variances of those K bell curves that make our observed data the most mathematically likely to have occurred.
To solve this, we introduce latent or hidden variables. For every single data point, there is a hidden vector of probabilities representing the chance it was generated by cluster 1, cluster 2, etc.
And just like K-means, EM is a tick-tock algorithm. It alternates between the E step and the M step.
Let's slow down and trace the E step, the expectation step, because this is heavy on Bayes' rule.
In the E step, you freeze the current shape of your bell curves. You take a single data point, and you want to calculate its posterior probability, the probability it belongs to a specific cluster, given its location.
So Bayes' rule says you take the prior probability of the cluster, how big the cluster is overall, multiply it by the likelihood of the data point given that specific Gaussian shape, how high the bell curve is at that exact point, and then normalize it by divide it by the sum of probabilities across all K clusters.
So that data point sitting right in the middle between 2 clusters. Under K-means, it was forced into cluster A. Under the E step of EM, the math says, based on the bell curves, this point has a 50% probability of belonging to cluster A and a 50% probability of belonging to cluster B.
It represents the uncertainty perfectly.
Then comes the M step, the maximization step. We freeze the probabilities we just calculated, and we update the parameters of our bell curves to maximize the likelihood. We recalculate the mean of cluster A, but instead of a simple average of the points inside it, we use a weighted average.
Right, so that point in the middle doesn't just jump into the calculation for cluster A. It contributes exactly 50% of its coordinate values to pulling cluster A's mean, and it contributes 50% of its coordinate values to pulling cluster B's mean. It softly influences both.
If we compare and contrast K-means and EM for the exam, the convergence properties are wildly different. K-means is guaranteed to mathematically converge in finite time
Why?
because you are assigning n discrete points to k discrete clusters. There is a finite combinatorial number of possible configurations. Since every step mathematically must reduce the error or keep it the same, you eventually run out of configurations and the algorithm terminates.
But EM operates entirely in the continuous realm of probabilities. A point can belong to a cluster by 50.1%, or 50.01%, or 50.001%. There are infinite configurations.
EM's math guarantees that the likelihood of the data will monotonically increase. It will never get worse. But because it can take infinitely smaller and smaller probabilistic steps, it might never mathematically reach absolute convergence. It just gets asymptotically closer.
In practice, we just set a tolerance threshold and stop it when the changes become microscopic.
And here's the beautiful unifying synthesis of this section. K-means is mathematically just a rigid, highly constrained, specialized edge case of expectation maximization.
Wow.
If you take the EM algorithm and in the E step you force the highest probability to 1.0 and round all the others down to 0.0, and you force all the Gaussian variances to be equal and spherical, EM instantly transforms into K-means.
That is exactly the connective tissue the professor is looking for. Okay, we have successfully clustered the rows of our database. We've grouped the data points together with probabilistic nuance. But what about the columns? What about the features themselves?
If you are dealing with modern data, like a high-resolution image or a genetic sequence, you don't have 10 features. You have 10,000 or a million. Grouping the rows is mathematically pointless until you can compress the column space.
Welcome to the final pillar, dimensionality reduction and manifold learning. We need to squish a 10,000 dimensional data set down to 10 dimensions without losing the fundamental geometry of the data.
The classic foundational starting point here is PCA, Principal Component Analysis. PCA is a linear transformation. It looks at the massive cloud of data and asks, in which direction is this data spread out the most?
It calculates the axis of maximum variance, it draws a rigid straight line through that widest spread, and calls that principal component 1.
Then finds the next widest spread that is completely orthogonal at a 90-degree mathematical angle to the first, and calls that PC2.
The lecture transcripts specifically demand a comparison between PCA and ICA independent component analysis. You might be tempted to think they do the same thing, but their mathematical philosophies are opposites.
It is a vital distinction. PCA produces a strictly ordered set of features. PC1 is mathematically guaranteed to capture more variance than PC2. And because they are orthogonal, they don't geometrically overlap.
PCA's entire goal is optimal reconstruction. It wants to compress the data in a way that allows you to rebuild the original data with the least amount of squared error.
But ICA doesn't care about variance or reconstruction error. ICA focuses purely on statistical independence. It produces a bag of features. There is no inherent order. Component 1 isn't more important than Component 4. ICA assumes your data is a mix of independent hidden signals, and it tries to unmix them.
The classic analogy is the cocktail party problem. You have 3 microphones in a room and 3 people talking simultaneously. The data recorded by each microphone is a chaotic mix of all 3 voices.
PCA would look at that data and try to find the loudest combined frequencies. ICA looks at the data and uses statistical moments, specifically looking for non-Gaussian distributions to mathematically isolate voice 1, voice 2, and voice 3 into pure independent channels.
Think of PCA as a heavy compression filter, prioritizing the loudest signals. ICA is a chemical separator trying to find the pure, independent ingredients.
And then, amidst these complex linear algebra techniques, the lectures introduce RCA, Random Components Analysis.
Which, on its face, sounds completely absurd. You just generate a matrix of random numbers and multiply your data by it to project it into a lower dimension. Why on earth does splattering random math at your highly structured data work?
It works because of the deeply unintuitive geometry of ultra-high-dimensional space. The math relies on the Johnson-Linden-Strauss lemma. In incredibly high dimensions, say 10,000 dimensions, if you generate random vectors, they are almost certainly going to be highly orthogonal to each other, just by pure chance. There's so much empty space that random lines rarely point in the same direction.
So by multiplying our data by these random, naturally orthogonal vectors, we project the data down to, say, 100 dimensions.
And the lemma proves that this random projection preserves the relative distances between the data points surprisingly well. Points that were far apart in 10,000 dimensions remain relatively far apart in 100 dimensions.
It is lightning fast, requires almost zero compute compared to finding the eigenvectors in PCA, and often preserves enough geometric structure for a downstream neural network to classify the data perfectly.
It's a brilliant hack. But PCA, ICA, and RCA all share one massive foundational limitation. They are strictly linear. They assume the geometry of the data is made of straight lines and flat planes.
But real-world data almost never lives on a flat plane. It lives on a complex, nonlinear manifold.
Think about the classic Swiss roll data set. Imagine a piece of graph paper with data points drawn all over it. Now take that paper and roll it up tightly into a spiral cylinder, an S shape, in 3D space.
If I ask PCA, or Standard Multidimensional Scaling MDS, to measure the distance between a dot on the inner roll and a dot on the outer roll, it calculates the Euclidean distance. It draws a rigid straight line right through the empty space, piercing through the layers of the paper. It completely ignores the fact that the data is constrained to the 2D surface of the paper itself.
And this leads to the dreaded crowding effect in dimensionality reduction. When PCA squishes that 3D spiral down to a flat 2D plane based on those straight line distances, points that were actually very far away from each other along the surface of the paper get violently crushed on top of each other, simply because they happen to physically overlap in the folded 3D space. The structure is destroyed.
So how do we fix the crowding effect?
Yeah.
We need algorithms that respect the manifold, that understand the paper. The first attempt in the evolution is salmon mapping.
It's essentially a weighted version of MDS. It modifies the loss function to penalize the algorithm heavily if it crushes small distances, forcing it to respect local neighborhoods. But because it relies on complex optimization, it is highly prone to getting stuck in local minima and is terribly sensitive to noise.
The real geometric breakthrough comes with IsoMap. IsoMap solves the Swiss roll perfectly by introducing geodesic distance.
Instead of drawing a straight line through the folds of the paper, IsoMap plays a massive game of connect the dots. It looks at every data point and creates a graph linking it only to its immediate k-nearest neighbors.
So it builds a mesh on the surface of the paper. Now, to find the distance between the inner dot and the outer dot, IsoMap can't jump through empty space. It has to walk along the graph. It hops from neighbor to neighbor to neighbor, tracing the exact curvature of the spiral.
By calculating the shortest path along that nearest neighbor graph, IsoMap physically unrolls the manifold. It flattens the S-curve beautifully, preserving the true distances. But IsoMap has a computational ceiling. Calculating the shortest path across a massive graph for millions of points scales terribly. It struggles with vast data sets and highly disjointed clusters.
Which opens the door for TSNE, T-Distributed Stochastic Neighbor Embedding. TSNE takes a completely different philosophical approach. It abandons rigid distance measurements entirely and uses probability.
In the high-dimensional space, TSNE calculates the probability that point A would pick point B as its neighbor based on a Gaussian distribution. Points that are close have a high probability of being neighbors. Points far away have almost zero.
Then it drops points into a low-dimensional 2D map and calculates those same neighbor probabilities using a different distribution, a student's t-distribution, which has heavier tails to prevent the crowding effect.
And the optimization goal is to arrange the points in the 2D map so that the probability distribution exactly matches the probability distribution of the high-dimensional space. And what mathematical tool does it use to measure the difference between those two probability distributions?
Kullback-Leibler divergence makes its triumphant return. TSNE minimizes the KL divergence between the high-dimensional and low-dimensional probabilities. For visualization, TSNE is a masterpiece because it excels at violently pulling complex, tangled local clusters apart so human eyes can see them.
But if you use it for downstream machine learning, it has severe flaws. Because it focuses so intensely on local probabilities, it often completely shreds the global structure. The distance between two distinct clusters in the TSNE plot means absolutely nothing mathematically. Furthermore, it relies on random initialization, meaning every time you run TSNE, the KL divergence optimization might settle in a different local minimum, giving you a completely different visual map.
Which brings us to the ultimate modern fix in this evolutionary chain. UEP, Uniform Manifold Approximation and Projection. UMA was designed specifically to fix the flaws of TSNE. Under the hood, it uses profound topological mathematics, but practically, it balances preserving the tight local clusters of TSNE while maintaining the broad, accurate global structure of IsoMap. And critically, it is vastly faster. able to handle massive modern data sets.
But the most important fix UMIT makes, in a great detail for the exam, is how it handles initialization. You said TSNE uses random initialization, which makes it inconsistent. UMA doesn't. UMP uses spectral embedding to create a consistent, mathematically sound starting point.
Let's explain spectral embedding so it's not just a buzzword. Before UMEF starts moving points around probabilistically, it looks at the nearest neighbor graph of the data. It builds a matrix representing all those connections, called an adjacency matrix, and uses it to construct a graph Laplacian. By calculating the eigenvectors of that Laplacian matrix, it mathematically finds an optimal, deterministic, low-dimensional representation of the graph.
It uses linear algebra to find the absolute best structural starting point, and then uses the probabilistic optimization to fine-tune it. That means if you run UMP 10 times on the same data, you don't get 10 random maps. You get a highly consistent, mathematically grounded projection every single time.
It is the culmination of everything we've discussed. It blends graph theory, linear algebra, and probabilistic topology into a single tool. Wow. We have covered an immense amount of ground today. But if we synthesize this deep dive, the mission we started with is complete. The connective tissue is everywhere. Every single algorithm was born because its predecessor hit a mathematical or computational wall.
We saw it repeatedly in every domain. In gradient optimization, plain SGD zigzagged in ravines, so we added Poliak's momentum. Momentum blindly overshot curves, so Nesterov added look-ahead gradients. Adagrad's adaptivity suffered from irreversible shrinkage, so ARM as prop introduced an exponentially decaying window. Adam tangled weight decay with adaptive scaling, so AdamW cleanly decoupled it.
In randomized optimization, hill climbing got trapped in local basins, so we added random restarts. Restarts suffered from geometric amnesia, so simulated annealing added a probabilistic cooling schedule. Genetic algorithms shattered under the locality assumption, so MIMC built explicit dependency trees using mutual information and KL divergence.
And in unsupervised learning, single-linkage clustering chased noisy trails, so K-means tracked the center of mass. K-means made rigid, arrogant mistakes on boundaries, so expectation maximization softened the boundaries using maximum likelihood. PCA crushed folded manifolds, isomap unrolled them with graphs, TSNE separated them with probability, and UAP balanced it all with spectral embedding.
The evolution of machine learning isn't a list of isolated equations. It is a constant, unending dialogue between the geometric complexity of the data and the computational constraints of our algorithms. We are always trading assumptions. We trade the assumption of a smooth, convex landscape for the chaotic exploration of randomized search. We trade the speed of a single point for the deep structural knowledge of MIMIC. We trade rigid, fast clustering for the probabilistic, infinite nuance of EM.
If we connect this to the bigger picture, you realize that these algorithms are essentially mathematical philosophies on how to handle the unknown.
Which leaves me with a final provocative thought for you to mull over as you prep for this exam. Think about the trajectory we are on. We are using incredibly tuned algorithms like AdamW to navigate the lost landscape of our neural networks. And we are using algorithms like MIMIC to mathematically model the structure of the optimization space itself.
We are getting closer and closer to algorithms that truly understand the topology of their own problems.
Exactly. So how far are we from an AI that doesn't just tune its own learning rate, but autonomously selects, tunes, and mathematically derives and writes its own novel optimization algorithms in real time based purely on the shifting topology of the problem it's facing? If the optimizer reaches a point where it starts optimizing the optimizer, what does that lost landscape even look like?
No, that is a foggy mountain I would love to see.
Okay.
Good luck in the exam.